All right, welcome everyone. Can you hear me? Can you see a slide that says Lecture 2 Math Review? Okay, great, thank you. So this is the second lecture for CS 189, the CDSS offering. Make sure you're in the right place. And before we start, a quick administrative notes. So I think I saw someone ask in the chat about updates for discussion sections. So discussion sections and office hours are starting next week, and you should be able to expect more information about that on Piazza within the next couple of days. There are still some sort of rough edges that we're trying to iron out, but you can expect both discussions and office hours to start next week with full details on Piazza over the course of the next couple of days. There's one exception to office hours, and it's as follows. So my office hours for this class are going to be a half hour after every lecture. So from 2 to 2:30 after lecture, and it'll be wherever lecture is. So if lecture is on Zoom, it'll be in this same meeting. And if lecture is in person, then we'll try to have it be in Evans, but we might get kicked out. And then in that case, we'll just spill out into the hallway or something like that. So the one exception is that next Friday I have a one-off meeting, so I can't hold office hours after lecture. So instead, I'll start my office hours today. So after this lecture, I'll be around for a half hour if anybody wants to ask questions about this course or the stuff that I talked about today or anything else. So let's talk about today's lecture. Today's lecture is Math Review, by the way. All of you probably saw that title. And what that means is I'm not really trying to teach you anything new today. Maybe some of these things you haven't seen before, but I'm not necessarily trying to teach them to you in any kind of detail. It's more about letting you know that the following mathematical concepts exist and are relevant to this course. So either you've seen them before and that's great and you just need to review them, or maybe you haven't and you need to go study them on your own. So if today's lecture has you feeling completely lost, then this course probably will be difficult. You don't necessarily need to know everything off the top of your head though. So maybe some things you've seen before, but some time ago, so you don't exactly remember what it is and you need to go review it. Maybe a couple of things that I talk about today you've never seen before and you need to go learn it. Those are all fine. You just have to know about that so that you're ready for the rest of this course. I should also mention that today's lecture is not comprehensive. I'm just trying to pick and choose some of the things that I think show up a lot in this class, but there are other mathematical concepts that are going to pop up throughout the course, and the same thing goes there. So if you haven't seen them before, it's going to be something that you're going to have to pick up on your own. The content in this lecture should help with Homework Zero, which is another diagnostic tool for you to understand whether or not your mathematical background is sufficient to get through this course. And Homework Zero is already out. It's on Piazza. So if you haven't taken a look at it yet, you should probably do that as soon as you can. So today we're going to go over, some topics in probability, linear algebra, and vector calculus, which are kind of the main mathematical areas that this course draws from. I will occasionally monitor the chat, although if you feel comfortable doing so, my personal preference is that you ask questions out loud by unmuting yourself. Are there homework slip days? No. There are homework drops though, 2 drops. Office hours for homework help. More details will be announced about that, probably at the same time that other office hour details are announced. Okay, so let's go into a little bit about probability, starting from something relatively foundational, which is random variables. So a random variable is sort of this thing that takes on different values depending on what the outcome was of a random event. So, something like if I flip a coin, maybe that comes up either heads or tails, and the random variable might denote the outcome of that coin flip. or a dice roll, or a random sample from a population, which is something that we'll see a lot in this course, and so on and so forth. There are a lot of different examples of what this might be. Random variables are typically denoted with a capital letter. So in this lecture, by the way, I am going to talk a little bit about notation, which will mostly try to stay consistent with throughout this course. But even within this course, and especially outside of this course, you might see notations that differ. And that's just something that comes with the domain. And you're going to have to get used to seeing notations that are a little bit different, but we'll try to keep it as consistent as possible as we're moving through this course, but no promises. So a sample of a random variable is basically when I measure it and then realize its value. So if I sample the outcome of a coin flip, it means that I flip the coin and I see whether or not it's heads or tails. And we'll usually denote these as lowercase. One thing that we'll talk about a lot in this class are samples that are independent and identically distributed. So independent, hopefully you know this concept of random variables that essentially don't have any influence over each other, and identically distributed in the sense that they come from the same, their underlying distribution are the same. And we'll often consider quantities such as expected value of a random variable, variance of a random variable, and we'll often rely on formulas such as Bayes' rule and Jensen's inequality and so on and so forth. So if any of these things don't sound like they ring a bell, it's good to sort of look them up and see whether or not you can digest what's going on there. Okay, so let's talk about this in a little bit more detail. So I'm going to pull out some board work. So as an example, let X, capital X, right, denote a random variable that's the outcome of flipping a biased coin. So that means that heads and tails don't come up each with probability 50%. This is some kind of weighted coin that has different percentages. So let's say that probability that the coin flip comes up as heads, which I'm going to mark as 1, is 0.75. So everybody can see that I'm writing on the slide. All right, fantastic. And then we'll say correspondingly that probability that this comes up as tails, which I'll note as 0, is 0.25. Okay, so if I have some kind of random variable that's distributed this way, one thing that I can say is that here X follows a Bernoulli distribution with parameter 0.75, which is the probability that it comes up as 1. So this little squiggly symbol here basically means X is distributed according to a Bernoulli distribution. Okay, so if I flip this biased coin n times for some number n, right, then what I can assume is that each one of these coin flips first is independent, so they don't influence each other, and 2, that they're identically distributed because I'm flipping the same coin over and over again, right? So the way that I can write that is I have different random variables, x1 through xn. Each one of these represents, a different flip. And then I can say that these are distributed IID according to this distribution, this Bernoulli distribution. And then if I wanted to know what is the expectation of my original random variable x, well, this is, oops. Looks like I've lost my annotations. Can everybody still see the slide? Or can I see the slide now? It's just blank, right? That is unfortunate. All right, maybe we'll change this setup in the future, but let's hope that there are no technical difficulties for the remainder. So I'll just write, I'll repeat a couple of things. So We remember this. And we remember P of x equals 0 is 0.25. We had x1 through xn as coming IID from this Bernoulli. Okay, and then the expected value here, right? Well, what's the formula for expected value? It's a sum over all the possible values of that value times the probability, right? So my two possible values here, which I'll denote as a lowercase x, are 0 and 1, right? And so if I multiply the value by the probability that x takes on that value, then I get 1 times 0.75 plus 0 times 0.25, which just gives me 0.75. Pretty straightforward, right? Now the variance, there's multiple ways that I could write down the formula for the variance. One of the simplest ones, at least to write down, is that the variance of a random variable x is the expectation of that random variable squared minus the expectation of that random variable squared. And in this case, that's going to be 0.75 minus, I already did this calculation, 0.5625, which gives me 0.1875. Okay, so one note that I do want to point out here is that we know, or we should know, that the variance of a random variable is always non-negative. And there are multiple ways that we can figure out that the variance is always non-negative. One way that we can do this is using an inequality called Jensen's inequality. And this inequality is of separate interest in this course. It's going to pop up quite a few times. So if you're not sure what that is, a good exercise is to go look it up and then see whether or not you can apply it here to show that the variance is always non-negative. All right. Any questions about this part? Good, let's get a little bit more advanced then.
So for the, sorry.
Yes.
Oh, for the expectation,
yes.
since it's I guess a Bernoulli thing. I know there's a simpler like formula for that, like we have for binomials, it's like NP or something. For the expectation, just for my own curiosity and like refreshing my mind, would there be a simpler way of expressing that isn't like exactly in probability notation? Because I know that I always kind of struggled to comprehend like x times the probability of random variable x, lowercase x, right? So just wanted to kind of like get some more clarity on that, just a refresher.
Yeah, right. So for a lot of the commonly used distributions, there is a simpler formula for the expectation. For Bernoulli, it's P, right? It's just the probability that that x comes up as 1, which was 0.75 in the previous example.
Gotcha, thanks.
Mm-hmm. And for a lot of the distributions that we'll use, like Gaussian and things like that, there are similar simple formulas for how you compute the expectation, and sometimes the variance as well. Okay, so in this class, we're going to also use some basic concepts from a field called information theory, which is pretty heavily embedded into probability theory. And information theory basically quantifies exactly what the name says. It's how much information is present in these random variables, and how do I try to quantify that? But that's not really super important for this course. What's important for this course is that you learn a few of the basic concepts from information theories, and then you know how to apply them to machine learning. So for example, we're going to talk quite a bit about the entropy of a random variable, which is also sometimes referred to as the expected surprise. I don't really love the term expected surprise. I think that it's kind of easy to misunderstand exactly what this means, but we'll try to understand what that might entail using the following graph. So suppose again that I'm flipping a bias coin, and in this graph here, the x-axis basically denotes what's the probability that that coin comes up as heads, and then the y-axis is entropy. Okay, so let's say that I was at one of the ends of this extreme. So either the coin never comes up heads or the coin always comes up heads, 0 or 1, right? Well, then I can think about what is the expected surprise of flipping this coin. Well, the expected surprise is 0 because I would be extremely, infinitely surprised if the coin didn't come up. If p of x equals 1 is 0 and the coin comes up heads, I'm extremely, infinitely surprised. Same thing goes for the other way, right? But that outcome never happens. And so because we're talking about expectations and that outcome never happens, it doesn't matter. And therefore, the expected surprise would then be 0. Whereas if I have, and this is where things start to get a little bit weird, if I have a perfectly balanced coin, so each outcome comes up with equal probability, then when I flip the coin, I really don't know what to expect. And so in some sense, whatever outcome happens, I'm sort of a little bit surprised all the time. And then when you take that in expectation, it turns out that the maximum entropy or the maximum expected surprise of a random variable is essentially when it's uniform, when it's perfectly balanced over all the different outcomes that could possibly happen. But again, expected surprise, I feel like, is a bit of a weird term, at least in my view, for how to view this particular quantity. In the next slide, we'll get into what the mathematical definition actually is of entropy. And then there are some other relevant concepts that we'll also go over on the next slide called cross entropy and Kullback-Leibler or KL divergence, sometimes also referred to as relative entropy. And knowing the mathematical definitions, as well as some of the basic properties and trying to get the intuition for some of these things is going to be important in a few parts of this class in order to fully understand what's going on when we get into actual machine learning concepts. So let's talk a little bit about these things. Hopefully this doesn't glitch out on me this time. So when we're talking about entropy, we're going to denote it with a capital H. I'm going to write up here just to give myself the most room because I write kind of large. And it's the entropy of a random variable x. Although as you can see on this slide, one thing that I wrote is that we also sometimes write the entropy of a probability distribution h of p. So for example, p could be the distribution that x follows. And we'll use those two notations interchangeably as long as there's no ambiguity. So sticking here with the first one, h of x, how we define that is the negative of the sum over all possible values, little x, that my random variable x can take on, of the probability of that value times the log of the probability of that value. Now, I know this probably looks a little bit weird. One way that I can also write this is the expectation of the negative log of the probability. And so this is why this is called expected surprise, because this quantity inside this expectation, negative log p, is what's typically known as the surprise. So you can imagine basically what this is saying is that the less probable a value is, the higher the negative log probability is. Okay, so therefore, I'm more surprised the less likely a particular value is to come up. Why exactly negative log p? Well, there are some mathematical reasons, but again, they're not really important for this course. So for example, for x sampled from the Bernoulli that we had before, we have that the entropy, and again, I already did some calculations here, is negative 0.75 times the log of 0.75 plus 0.25 times the log of 0.25. Now you might be asking, what's the base of this log? Sometimes it'll be in base 2, in which case entropy is measured in what we call bits. Sometimes this log is base e, so the natural log, and then we call them nats. If we use log base 2, then what we get is approximately something like 0.811 bits is the value of the entropy for this particular random variable. Okay, so that's entropy. Hopefully it looks familiar to some of you. If not, it's a good quantity to know. And we'll try to gain some more intuition about what the entropy is actually saying as we move through this course. There's also two other terms that are good to know. First one is cross entropy, which is confusingly, we also denote it with an H, but we distinguish it by the fact that it takes two arguments. And here I'll write them as probability distributions for convenience. So P and Q. The cross entropy between two distributions P and Q is defined as the negative sum over all possible values of P of X times log Q of X, which is equal to the expectation under P. So if I write a subscript of my expectations, it's denoting which distribution the random variables follow times negative log Q of X. Okay, so why did I write a subscript on this expectation? Well, it's because the random variable inside the expectation is X, right? But here, what we're saying is that maybe X comes from P or maybe X comes from Q. And so just writing P makes it clear that we're talking about the random variable X being distributed according to P. And so cross entropy we can think of almost like a measurement of sorts of how similar P and Q are. So basically, if P and Q are the same distribution, right, then actually what we get is that the cross entropy is going to be just equal to the entropy, right? So H of P and P, if you look closely, if you replace Q with P, then H of P and P just becomes the entropy of P, right? And then turns out this is actually the minimum value that the cross entropy can take on. And if Q is any distribution that's different from P, then we're going to get a larger cross entropy value. There's another closely related concept, which is called KL divergence, which is the last thing that we'll talk about related to information theory, which we write as D subscript KL. And it follows this little kind of funny notation where we have two distributions still, P and Q, but we draw two bars between them for some reason. So the KL divergence between P and Q is defined as no negative sign, right? The sum over all possible values X, P of X times the log of P divided by Q. Okay, so what the heck is this thing? Well, it turns out if you do a little bit of algebraic manipulation, this thing is equal to the cross entropy of P and Q minus the entropy of P. Okay, so why is this useful? Well, the reason why this is useful is because remember what we said, the cross entropy is equal to the entropy when P and Q are the same. Otherwise, it's bigger, right? So we can immediately conclude from that the KL divergence is always non-negative, right? Because the cross entropy is bigger than the entropy. And the KL divergence is zero when P and Q are the same. So essentially what we can think of is that KL divergence is, one way that we can sort of intuitively measure how similar are two distributions P and Q from each other. If they're exactly the same, KL divergence is zero. If they're not the same, KL divergence grows. What's important here is that KL divergence is actually not a proper measure of what we call distance because it's not necessarily symmetric. So KL divergence between P and Q is not necessarily the same as KL divergence between Q and P. There are other ways to measure similarity between probability distributions that are symmetric, which makes them proper distances. KL divergence is not one of them, but it does turn out to still be very useful when we're trying to think intuitively about how similar are two distributions P and Q. And then as an aside here, this has really nothing to do with anything that I've written on this slide, but it's also very important for you to know and will come into play when we talk about concepts in information theory is a concept known as Monte Carlo estimation. So Monte Carlo estimation is just a general probability thing that you need to know. And basically all it's saying is that if I want to know the expectation under some distribution P of a function f of a random variable x. Well, that might be really hard to compute on its own, maybe because it's really hard to do a summation over all the different possible values x. Maybe it's actually an integral if x is a continuous random variable. Maybe these things get a little tricky. But if it's easy to draw samples of x, so let's say I can draw x1 through xn, all iid from the distribution P. If I can do that, then I can say that this expectation will approximately equal the average over the samples that I draw of the function evaluated at those points. So if I have I equals 1 to n, and I evaluate at, really? So close to done. Sorry about that, everyone. We'll figure out a better setup for next time. All right, sorry if anyone was not quite done with writing down everything that I had before, but we're just going to start from Monte Carlo estimation. Everyone can see my screen, right? With the blank slide on it. All right. Figure this out for next time. So if I want to estimate the expectation with respect to a distribution P of f of x, I can approximate that with an average of f evaluated at samples of x, where every sample is drawn iid from P. Okay. Any questions? I'm looking through the chat right now. P and Q or distributions, not just probabilities of success.
That was in response to what someone asked earlier. If you scroll a little bit higher, someone asked.
Got it. Yes, P and Q in general can be, in general can just be arbitrary distributions, not necessarily, distributions over only Bernoulli's. That's just the earlier example that we used. Can you explain the difference between KL divergence and cross entropy? Well, mathematically, essentially KL divergence is only different from cross entropy by a factor of the entropy of P, which is the first distribution that you pass in as an argument, right? So if P is some fixed distribution, then KL divergence and cross entropy are actually the same minus some constant, which is the entropy of that distribution. So they're similar concepts. KL divergence is just kind of nice because it's sort of grounded at 0 when P and Q are the same, whereas cross entropy is not, and it's non-negative in general. Struggling with what cross entropy means on a higher level. So I think that's okay, because cross entropy is a little bit strange in terms of, I don't really necessarily know if there's a great intuitive meaning. Maybe someone has one, you're welcome to chime in, but I sort of just view it as a quantity that we're going to find useful later on when we're trying to interpret other things that we actually want to understand on an intuitive level. So as long as you sort of, write down the equation, or I guess the equation is not here anymore. Hopefully if you wrote down the equation when it was here, then you'll be okay. And then we can figure out intuitive meanings behind things later on. And again, we'll sort out these we'll sort out these technical difficulties for next time. Okay, so let's leave probability behind and hopefully get into something that works a little bit better and talk about linear algebra. So linear algebra is quite important for this course. There's quite a few concepts that we want to cover here, and it also bleeds into the next part, which is vector calculus, which we'll also need a few basic concepts from. Let's start really basic from linear algebra. So what's a vector? Well, a vector is a quote unquote one-dimensional row or column. You can sort of think of them as like arrays of numbers. And the reason that I put one-dimensional in quotes is not because it's not one-dimensional. In some sense, it is. The reason is because when we use the term dimension in this class, usually what we're actually going to be referring to is the length of a vector. So we'll say that a vector is like k-dimensional if it has k numbers in it. But I wanted to use one-dimensional here in terms of specifying that it's just a single row or a single column, and it doesn't have any additional spatial dimensions that it lives along. As opposed to something like a matrix, which is typically thought of as a two-dimensional quote-unquote table, although again, that's not how we'll usually use the term dimension in this class. And then sometimes quote-unquote higher dimensional objects are called tensors. So if I have like some kind of like 3D table looking thing, then I'll call that a tensor. Although, sometimes people still call those matrices depending on whether or not they really care about terminology. Vectors, matrices, and tensors are all typically denoted with bold and non-cursive letters whenever possible, as long as it's not confusing. And typically that's what we're going to stick to in this class as well. And vectors are typically denoted with lowercase letters, and matrices and tensors are typically uppercase. One side note that I wanted is that in this class, we're going to use subscripts for a lot of different purposes. So you're about to see the second one. So the first one, from the probability part of these slides, subscripts were used to do, actually maybe different realizations of the same ID random variable, right? So if I have x1 through xn, and those are all distributed the same, that was one use of subscripts. And then in linear algebra land, the subscripts are typically used to denote different entries in a particular vector or a particular matrix or something like that. And so try not to get confused with all the different ways that we use subscripts. Usually it should be fairly clear from context. So let's try this one more time. All right, so we have, for example, I could say I have a vector u, and we'll write this as a row vector, and this consists of, for example, numbers u1 through ud. Well, what I call this, I would call this a d-dimensional row vector. It has d entries in it, it's calling it d-dimensional, and it's a row, d-dimensional row vector, right? I could also have something like a vector v, and maybe it's laid out as v1 all the way through vk. What is this thing? It's a k-dimensional column vector, right? It's got k entries in it, and it's laid out like a column. Okay, so one fairly important concept that we're going to see regarding vectors and also matrices later in this class, and also probably something that you've already seen on homework 0 if you've taken a look at it, is this concept known as LP norms. And so LP norms is sort of generalization of some norms that you probably see all the time, like L1 norm and L2 norm. And basically, the LP norm of some vector u, which we denote with a little subscript p, and these two lines, is equal to the sum over all of the entries. So in this case, if u, for example, is d-dimensional, this sum would go from I equals 1 to d of the absolute value of that particular entry to the pth power, and then this whole thing to the 1 over pth power. Okay, so what are some examples? Well, you've seen, for example, L1 norm probably. So if I substitute p for 1, right, then all I end up getting is just the sum of all the absolute values of those vectors, or sorry, of the entries in that vector, right? What about L2 norm? this is probably the one that everybody's the most familiar with, right? I get the square root of the sum of squares, right? So LP norm is just a generalization of, these very common norms that we use all the time. They're also, this also encompasses things like L0 norm, L infinite norm, things like that. But L1 and L2 are definitely the ones that are going to be most common in this class. Okay, so we also have matrices, right? So these are typically denoted with capital letters. And for example, I could have some matrix that's like, like A11 all the way over to A1M. Maybe down this way, I have AN1. And over here, I have, of course, ANM, right? So what is this? This is an N by M matrix, right? So the height first and then the width, N by M matrix, right? So over here, we have a few things that are important to know. What's a square matrix? Well, it's when N equals M, right? So that becomes a square. What's a symmetric matrix? Well, it's a square matrix where I have Aij is equal to Aji for all I and j, right? Another way that I can write this in matrix notation is that A equals A transpose, right? And then a concept that's going to be important in this class that you may or may not have seen before is this concept known as the positive semi-definite matrix, which is a matrix square and symmetric that satisfies the following criteria, where X transpose AX, by the way, this thing is called a quadratic form. This thing is greater than or equal to 0 for all X. What do I mean by for all X? Well, A, in this case, let's say is like N by N, right? Then X is any n-dimensional vector, okay? And typically, if we write X transpose AX, we're saying that it's an n-dimensional column vector, although I'll let you in on a dirty little secret. Oftentimes, we don't really distinguish that cleanly between row vectors and column vectors. We say that the vector is a column or a row depending on whatever is most convenient for us. But here, X would be an n-dimensional column vector if A is an n by n matrix. And we're saying that any such vector in this quadratic form is greater than or equal to 0 if A is positive semi-definite PSD. And this also extends to other definitions like positive definite, where the greater than or equal to changes to a greater, except for 0 vectors, and negative semi-definite, negative definite, et cetera, although PSD is kind of the most important one for this class. We'll also talk a little bit in this class about things like the trace of a square matrix. So that's denoted TR. And the trace of a square matrix A is just the sum of the diagonal entries of that matrix. I know that looks a little simple, and you might wonder, what's that even used for? Turns out it's quite useful for quite a few things. And so we'll get into where exactly that's used for, not just know that that exists. We can also talk about norms of a matrix, although this gets a little bit more tricky. And so we won't really generalize too much the way that we talk about matrix norms. We'll just talk about a couple. The first one being perhaps the most commonly used matrix norm, which is the Frobenius norm, which we denote as, again, these double lines and then subscript F for Frobenius. And that's equal to the sum, there's a square root out here. That's equal to the square root of the sum over I and the sum over J of Aij squared. So take the matrix, square all of its entries, and then sum all them together and take the square root. So it looks a lot like an L2 norm, right? Just sort of for matrices. As it turns out, this is also equal to the square root of the trace of A transpose A. So A trans multiplied by A, matrix multiplied. And that's sometimes a useful little identity. Someone's asking questions about homework 0. Let's leave that to office hours, which will happen right after this. Why is PSD a useful property? Good question. PSD is a useful property because sometimes we really care about quadratic forms, such as X transpose AX. And if we can write that that equals 0, sometimes that's kind of the property that we need. Another reason is that PSD matrices enjoy some pretty useful other properties, such as the fact that they have real positive, real non-negative eigenvalues, and stuff like that also turns out to be quite useful in certain contexts. What's the subscript for Frobenius norm? F, capital F. For the case of a square matrix, is that AII? Yes, it is. Sorry if my writing is a little bit wacky. Fantastic. Let's talk a little bit about important and, in my opinion, confusing concept called eigenvalues and eigenvectors. And these are, concepts related to square matrices. And we'll talk about a little bit about what eigenvalues and eigenvectors are on the next slide. But hopefully everybody has seen this in some context or another. Otherwise, it might get really confusing, because I'm not trying to give all the info behind what these objects are. I'm just going to give the definition, and hopefully we can work with that as the course progresses. Something that you might not have seen before, but if you've seen eigenvalues and eigenvectors, this will come relatively naturally, I think, is a concept that applies to all matrices, which are known as singular values and singular vectors. If you've seen this before, great. If not, we'll describe what it is on the next slide. And the next slide comes. For a square matrix, we can write something like A V equals lambda V. And if this equality holds, then V is what we call an eigenvector for the matrix A, and then lambda is what we call an eigenvalue. Okay, so V is a vector, right? If A is n by n, then V is an n-dimensional vector. And lambda is a number. It's just a scalar, right? And lambda is what we call an eigenvalue if this equality holds. Now, typically, just for convenience, we write eigenvalues in non-increasing order, right? So if A is n by n, there can be up to n eigenvalues, lambda 1, lambda 2, so on and so forth, all the way up to lambda n. And typically we'll write lambda 1 is the largest value. So we'll just, order all the eigenvalue. We'll order all the eigenvalue eigenpairs based on in decreasing order of the eigenvalue magnitude. Now, for any matrix A, not just square matrices, we have this concept called singular values, which we usually write with a sigma. So the ith singular value of a matrix A, let me label that. This is the ith singular value of A. Okay, so the ith singular value of a matrix A, any matrix, right, is equal to the square root of the ith eigenvalue. Let me write a little cleaner. Ith eigenvalue of A transpose A, which, as it turns out, is also equal to square root of the ith eigenvalue of A transpose. It turns out transpose A and A transpose have the same eigenvalues. And if we order them in non-increasing order, then obviously they're all the same. And the square root of these eigenvalues give us what we call our singular values for any matrix A. I'll pause here. Oh, and if anything needs to be repeated because something laggy, just do let me know if anything was if anything was missed. Apologize for that. Okay, so why do we care about singular values? Well, there are various reasons that we can care about singular values. One of the most important ones is what we call the singular value decomposition, or SVD, of a matrix A. So this turns out to be a really, really useful way to work with basically any matrix, or I shouldn't basically, it's really useful to work with any matrix because what we can do for any matrix A is that we can write it as U sigma V transpose if we choose these carefully. So what's cool about this is that sigma here is a diagonal matrix. What is a diagonal matrix? It's a matrix where all the things that are not along the diagonal are zero, right? Sigma is typically also thought of as a square matrix, although it doesn't have to be depending on how we characterize these things. And sigma II is equal to the ith singular value of A. Okay, and then what makes the SVD so useful is the fact that U and V are both orthogonal matrices. Okay, what is an orthogonal matrix? An orthogonal matrix is a matrix with columns that are all, wait a minute. So an orthogonal matrix is a matrix such that UTU, U trans U equals U transpose, which equals I. And really that's the property that's going to make orthogonal matrices useful. I'm having a brain fart here, but that is the useful property here. Okay, so then the last thing that we'll talk about related to eigenvalues, eigenvectors, and singular values is something called the spectral norm, which we take a matrix A, any matrix, and then we write, this actually for some reason has subscript 2. That's just the normal way the spectral norm is written. And this is actually equal to the largest singular value of A. And it turns out that this quantity here, the spectral norm, is actually going to be useful when we're trying to analyze certain properties of matrices. Basically, like I've done throughout the rest of this lecture, this is going to get glossed over. And then, once we actually reach this concept in the context of machine learning and what we're trying to do, then you'll figure out why this thing is actually useful. For now, it's just good to know that this exists. Also, something I didn't mention on the last slide, but I can mention now, is that the Frobenius norm can also be written as the square root of the sum of the squared singular values of a matrix A. That is another way that we can write Frobenius norm. Okay, I have 2 minutes, so let's let us get to some vector calculus, and if needed, we can finish that up next time as well on Monday. So it's important in this class to know about concepts in vector calculus such as gradients and Hessians. You may not have seen these before because I don't think there's a great class or resource that really teaches these things. But if you've seen multivariable calculus and linear algebra, then these things will come relatively easy as long as you can cut those concepts together. So basically, if we think about functions that have vector inputs and scalar outputs, what does that mean? It means that some function f takes in a vector x and then outputs a single number, a scalar y, right? Then the column vector of partial derivatives for that function is what we call the gradient. And something that's a little bit less important, but is also kind of useful to know, is that if that function doesn't output a scalar, if it outputs a vector instead, then we no longer have a vector of partial derivatives, we have a whole matrix of partial derivatives for each entry in the input and the output. And that's usually referred to as a Jacobian matrix. Although that's not really something that we're going to talk about a lot in this class. It's just useful to know sometimes. One way that we can characterize something called the Hessian, which is a matrix of all the second partial derivatives, is that it's the Jacobian of the gradient function. Although we'll see an easier way to sort of write down what the Hessian actually is right on the next slide. And a really useful reference when it comes to figuring out how to compute the gradients and Hessians is the matrix cookbook. If you've never heard of it, there's a link here and you can go check out section 2, and it has a lot of useful identities that that are just all written out very cleanly so that you can go take a look at it. I'm actually out of time. There were some technical difficulties, so we didn't quite get here, but on Monday, I'll have those resolved, and then we'll go over exactly what the definitions of gradients and Hessians are. Sorry about that, everyone. So we'll try to clean that up for next time, and we'll start here for the next lecture. And again, if anyone does have any questions about what we did, I'll still be around for half an hour, and then we can talk about those things. All right, so we'll pick back up next time. Thanks, everyone.